So, welcome back. We have 1 hour left, so we're almost done. I would like to continue the discussion about these flame wall interactions based on now the methods that we have discussed earlier, which are the simultaneous measurement of a gas velocity by particle image velocimetry and simultaneously to that the flame front position, as you will see in a second, that can be used as well to extract reaction rates or mean reaction rates, to be more precise. And I will show how to use nanosecond row vibrational cars together with a technique for looking for CO concentrations quantitatively based on a 2-photon excitation scheme that I will as well briefly discuss. And here in the CO concentration measurements, that is then relying on a calibration where all these effects of quenching and so on are included into the calibration method. And cars and this 2-photon LIF for probing CO are pointwise at low repetition rates, whereas the planar imaging techniques have been as well operated at higher repetition rates. So we've seen that view graph again earlier this week. Here it's shown again. PIV based on these particles that is not easy to be seeded to these flows. And our observation as well is getting a good seeding density close to the walls is not easy. So there the seeding density very often is lower than you would like to have it. Yes? So the question is whether the particles are tracked in vertices such that you have locally, let's say, a smaller density. Yeah, that's your question. Yeah.
That's what I think is that because in your boundary, your vortex also has a boundary layer. Your vortex will be tracking the particles.
Possibly. I think the exchange rate between the bulk and the boundary layer is not so high as well, such that you have a limited transport to that area, which is normal to the wall, and maybe that is as well a reason. I'm not absolutely sure in the end what the reason is, but the observation as well from others is that close to the wall the seeding density varies and is typically smaller. Okay, we have seen that as well. So you do this correlation to deduce the velocities. That is combined with the OH PLIF. We have seen that as well earlier this week, where you excite at 283 and then fix your laser at a certain transition and measure the relative intensities in OH, where you visualize the flame front. Quenching is not considered typically, but the intensity profile typically is considered. And so to remind you of that, then you take a laser and you fix it then to some frequency somewhere maybe here. Oops, maybe too far, go back. And then without furthermore scanning, do these experiments, looking for the typically redshifted fluorescence. And that is now transferred. So this is clear, I think, for PIV and OH PLIF. Yeah? Tracking the velocity simultaneously with the flame front in a plane. We're back to a plane. In a fluorescence scheme for CO, it is done a bit differently. And it is differently because the electronic levels, the electronic ground level, X, and the first electronic excited state of COA, they are separated by a huge energy gap. If you would try to overcome that with a single photon, you would have to go deeply into the UV. And that means you cannot access there any atmospheric conditions, because already if you would create this deep UV radiation, it would not be transmitted easily through the atmosphere of air, because it becomes intransparent below roughly 200 nanometers. And that's why for CO, a different scheme has been used for many years, back to the 80s, where, for example, Marcus Alden was among the first, to my knowledge, but as well people like Ron Hansen, when I remember correctly, using a 2-photon excitation. So that means you excite not the first electronic state A, but by the simultaneous absorption of 2 photons at around 230 nanometers, you can overcome this huge energy gap between the X and the B state, which is separated corresponding, if you would have a single photon, at 115 nanometers. instead of using that deep UV, you're using here 230 nanometer photons, which can be more easily generated in a normal dye laser after frequency doubling or tripling or frequency mixing. And that radiation, 230 nanometers, can as well be transmitted through air and through the flame. And then you excite that B state, and from that B state you wait for the fluorescence to occur into the A state. That is indivisible. This is a single photon process always. Such that if you would, of course, you have as well B to X transitions that are as well allowed. But what would happen if you have such a photon being so deeply in the UV, what you would expect? Scattered. It will be scattered. It can as well, but as well absorbed. Yeah, it will not come very far. It will be directly absorbed. And so what you then outside the flame can still observe is that fluorescence between the B and A state. There you have a progression of bands shown over here. This is the fluorescence from B to A, all of that the same, but from 0 to 1, 0 to 2, and so on, you have different locations spectrally where you can do the measurements. And then using a certain filter, maybe you just cut out one specific band. We're using the band around 480 nanometers. That must be this one over here. And then here you see a CO absorption spectrum. Shown is the X to B transition from here to here, using shown here for the Q branch, where you see the different rotational lines that are involved with that transition. And then you go for a certain specific transition that allows you to monitor CO with a reasonable signal to noise at low temperatures and high temperatures. So you take an intermediate Q value where you not only focus on high temperatures, but as well, as I said, for temperatures close to the wall that are then clearly below 1000 Kelvin. And then you do a calibration. In the calibration, you do that in a heated flows and as well in a laminar flame, where you know exactly the CO concentrations from 1D simulations. I shouldn't say exactly, where you have a good estimate of the CO concentrations. And you do that calibration in dependency of the temperature. That is the parameter that you have, as I mentioned as well, you always have to measure simultaneously, such that you have a calibration polynomial that is dependent of the temperature and links your CO signal with the number density of the CO. Yeah, and that is here from calibration. And that is then valid for a certain equivalence ratio when operating premixed. And you combine that with cars. I just remind you of this process, which is a nonlinear process based on the nonlinear polarization here of third order with the quantity, this chi3 tensor containing the information about the Boltzmann distribution. You have to fulfill the energy balance, as we have discussed earlier. You have to fulfill the momentum balance, the phase matching, such that then you create a beam in a certain direction containing all the information in this geometry here in this spectra. For example, once again, calculated spectra with the dispersion we have for 300 Kelvin up to 2400 Kelvin, where you see for higher temperatures really a fine structured spectrum with all these rotational vibrational transitions that after fitting that you receive then over the Boltzmann distribution a rather accurate and rather precise temperature value. In that experiment, it was the precision at 2000 K was in the order of 45 Kelvin. Yeah, it can be better if you use a better pump laser. Ours it was not injection seated. Okay, and then you throw everything together. You have here a YAG laser pumping the home-built broadband dye laser. You create here these three beams: the pump, and the Stokes. Then you have another pump laser pumping another dye laser, a commercial one, to create the 230 nanometers. They come here from the side, and in that case we have used a tiny mirror to reflect now as well the CO beam at 230 nanometers at the same volume. Then the Cars beam is directed here to the spectrometer, And perpendicular to that, you see here the intensified CCD camera looking for the CO fluorescence. And so these beams have been matched such that they were directed through one pinhole that was checked as well with the beam profiler. And later on, you match as well the CO probe volume to the size and shape of the car's probe volume. And thereby, you can achieve then, I refer here to that side, you can get a rather good resolution in wall normal direction with cars. We could, in principle, go down to 50 microns. With CO, we could go down to 100 microns. And that was the limiting here, such that all the data to be shown are 100 microns from the wall. And the precision, depending on the temperature, is at high temperatures here around 2.5%, at lower temperatures for cars around 8%, because you don't have these fine structures anymore. And for CO, it's in the order of 10%. With an accuracy, we estimated in the order of better than 20%. So it is not perfect, but it is okay, I would say. And that has been used simultaneously as well, as you will see later, with flame front position imaging, as well as in an additional set of experiment, the velocity has measured with the flame front position. Yeah? I will not go into all these details over here. Maybe that leads us too far. Have a quick look into head-on quenching, where maybe I should, because of time, restrict myself only to the flame dynamics. What you see over here is, once again, the experiment. It's ignited, the flame propagates, and then comes into the region of interest. Again, here the Reynolds number, mainly we have done that with Reynolds 5000, different equivalence ratios, doing without turbulence grid being laminar, with turbulence grid being turbulent. And that is a situation which is very close to what you would expect in an engine, at least at early stages of flame wall interaction. And that is now shown over here. You see here chemoluminescence imaging. There's some remaining me-scattering particles that was included in that flow, but I would like to point your attention only here to the chemoluminescence, which is showing that the flame initially is faster, and then by the action of the wall is getting slower until it then finally is extinguished. To the right-hand side, you see, after post-processing the flame from OH, and overlay to that the velocity. And that is, again, showing that things are getting slower when approaching the wall. And it is well nice to see what these velocity vectors do. Due to the expansion, they change direction, yeah, as you would assume. And as well, what is nice to see that the stagnation point of the flow is as well influenced. I can't see it here, somewhere here. It's not perfectly symmetric here. For that realization, maybe something has been slightly misaligned. Okay. Here you see the same as before for the laminar case. If you have the turbulent case, then you see here the wrinkled flame during its approach. And it's nice to see by the action of the wall, everything is laminarized. Yeah? The wrinkling disappears, everything gets slower, and the scales are in the flame are getting in this case here, larger. So, an initially turbulent flame becomes thereby stepwise laminar. And then, of course, it's interesting, as I said, to have a closer look into this CO and temperature during that head-on quenching. And the bad thing is here, we can't do it at high speed. We can do it as well only point-wise. That's why we have to do it somehow statistically phase-averaged. And so what you do is you fix your CO temperature location somewhere close to the wall, maybe 100 microns, and in the next set of experiments, maybe 200 microns, and so on, to get here step by step a wall normal profile. And then you take the data relative to the spark time. Because if the spark, if you take the data when the flame is not yet there, that's maybe not the interesting part, but then you wait until the flame is there and you take the data and repeat that for that time lag between spark and taking data. Staying at the same position, then you wait for a longer time lag between spark and taking the data. And thereby you get point-wise something like a phase averaged results with the relative to the spark timing. And you can imagine that takes a long time. Yeah, if you are heading for 200 realizations, for example, then you have to repeat that for each location and for each spark timing distance, you have to repeat that. And so that's why I concentrate only here on a small region where actually something happens, roughly in a very thin layer, which is here from 100 microns over 2, 3, 5, 900 microns to 1.7 millimeters. And what you see here is now the mean flame position. What you see here is the mean temperature. That was for laminar conditions. You see the mean CO concentration. And now, and this is the time. And time 0 is where you have then quenching. And so the flame approaches. The mean temperature goes up. The mean CO goes up. Of course, you do have here a certain gradient because there is some intermittency. Although it's laminar, not all experiments are identical to each other. Maybe the spark location changes slightly, things like that. So you go further. Now you have here, for this probe sample, at this time, 4 milliseconds prior to extinction, already reached nearly the adiabatic flame temperature in average. Now you reach here this 900 microns position, where now the temperature is sensing the flame as well. CO shoots up, and the same holds true now for those conditions. Now we are very close. And already what you see here from half a millimeter to 300 microns to 200 microns, the mean temperature is significantly lower because of heat transfer, as well as the CO production has decreased in mean. Interesting enough is that the CO consumption has not gone that far down. So here's something happening, leaving around less oxidized CO. So here the oxidation reactions are terminated such that in the end you have a higher CO emission. That can be traced back to these DNS calculations. You have a flame approach, you have quenching, and then you have a post-quenching period where then you have here, due to heat conduction, of course, as well, due to convection, then a decaying temperature. Okay, so that's already giving us some insights. Maybe I skip that because I will go into more detail into the scatter plots and the sidewall quenching and referring to the remaining time. It's maybe not good to do it here. But the idea is to use the data then as well point-wise and come up with scatter plots. As I said, that will be discussed later on. I would prefer to have a bit more detailed discussion the remaining half hour or so on sidewall quenching. Because here we do have the benefit that we have a statistically stationary flame such that we can take easily more data. And what I will discuss first is again using this planar data to come up with mean reaction rates. Okay, so first of all, you see here after post-processing what is the data looking like. You see here to the left, that's the wall. You see the flow field with the directions given by the arrows and the velocity magnitude by the color coding. And you see here this red line. This is after image post-processing the flame front, and the end here is where the flame has been quenched. Yeah? So when it comes closer and closer to the wall, you nicely see the quenching. Within the limit of resolution of the PIV, not every arrow is shown because that would be overfilled. But you see as well here this blue region. This is the velocity boundary layer. Not very well resolved, I admit, but after the quenching, you see how the velocity boundary layer develops. And that develops fast because of the higher viscosity over here. Yeah? And you see as well that this boundary layer, already you see that. We just submitted a paper with more resolution on that. But what you see as well, that the boundary layer is squeezed by the approaching flame. If I run that, you see, although that is laminar, it's not perfectly stable. Any idea where that comes from? Has anyone worked with these kind of bottle-shaped nozzles? I think this is a Helmholtz resonance. Yeah, where we tried to overcome that with different measures. We couldn't reduce it to 0. Although it's laminar, there is a remaining frequency that is measured not only here at the flame tip, but as well at the nozzle exit. Yeah, and that is due to this bottle-like shape that creates low frequencies. And this gives rise to remaining fluctuation at best that is maybe something plus or minus 150 microns. And so that's why, unfortunately, whenever you do any experiments as well with point techniques, yeah, and 150 microns matters, you need to know where the flame front instantaneously was. And that means the COT measurements in the end needed to be done simultaneously with flame front tracking. In the turbulent case, now you have this grid installed. Everything is more dynamic. The same equivalence ratio, and you see here the flame quenches further upstream. Yeah, of course it changes here with time. You see here the wrinkling is reduced. It's getting laminar, like in the head-on quenching. Although it's not too turbulent, it's the turbulence level is around 6 to 7%.
This is a simulation? No.
No, that's no simulation. It's a real measurement. That's real. It looks cool. I got this question as well from other people visiting the lab. They couldn't believe that. It's with limited resolution. That's real. Yeah. Okay. Good question. After 1 week, we are in an experimental class here. Okay. How did we deduce the flame front? Maybe a few words, because I know some of you are interested in post-processing. Again, it's not the best method. You see here our limited signal to noise that was at 10 kilohertz. You see the noise from the amplifier. However, using here a Kenny edge filter was good enough to track that front over here. Kenny edge filters are documented in literature and as well are available, for example, in MATLAB Toolbox. Then we have looked for we know now where the flame, or we have a good estimate where the flame front was. Then we can take a flame normal gradient and plot the gradient along that line S. Yeah, this S, this red line is shown over here. Of course, you do have some noise, but then eventually at some point you see a drop in this wall normal gradient. And this point where it has reached after normalization 50%, we simply defined as quenching. And that is, go back, here you see where we cut that off. And there we say this is a quenching point. Seems to be reasonable. Of course, you can now discuss. If you do it differently, maybe you have a different location, but we do that consistently for all the measurements. Once you have done that, you can come up with a quenching probability. Now, this is shown for the turbulent case. You look for those, this is the quenching probability from 0 to 1 at a certain axial distance from the nozzle. At 34 millimeters, for example, you never observe this location where this criterion is fulfilled. That's why you have a quenching probability of 0. If you're far downstream, you would never find a flame. That's why the quenching probability is 1. And because of the turbulence character of the flame, you have a certain transition between 0 and 1, which in our case here spreads over something like 10, 12 millimeters. And that is now used to deduce the flame brush, here for the laminar case, here for the turbulent case. Maybe we stay with the turbulent case, which I just discussed with the quenching probability here. Then you see here the mean flame front position. And in color coding, you see the probability of seeing the flame front somewhere there. And so that is then the probability of unburned gases is dark. The probability of burned gases is white. And so at this side, you always have the flame. That's why it's white. And then you see here it starts to deviate from white. That is the region where the flame actually bounces back and forth. And that is then the flame brush. And the flame brush, of course, is influenced by the wall. I'm sure, of course, already here at this position, but it's getting thinner and thinner and thinner. Yeah, as well expressing the laminarization of an initially turbulent flame. At the laminar case, we do have here the unburned, and here the transition from unburned to burned is steep. Yeah, we have the remaining fluctuations. That's why it's not a step. So the quenching probability is here given, but it's limited now to something like a millimeter or something, or less a millimeter. Okay. Now we have a global idea what the flame's dynamics is. Now we want to do something quantitative with that data. And what I show is how to use the data to get access to the mean reaction rate. The mean reaction rate is an important quantity in modeling of these turbulent flames, and of course is prone to interactions between the flame itself and the turbulent flow. And to calculate that, we need the local consumption speed, SL, and the flame surface density. And that is an expression taken from combustion modeling, where you see the mean reaction rate being dependent on the density and the fuel mass fraction of the unburned gases. That is known. So we know the density, we know how much fuel we put in with our mass flow controllers. And then we need somehow this local consumption speed that is influenced by the wall. And we need the flame surface density. The flame surface density is the surface of the flame per unit volume. Okay, and herefore we use, as you will see, the qualitative OH PLIF and the quantitative PIV. So how do we do that? First of all, the flame surface density, of course, in reality is a quantity, a density in a volume. Yeah, sorry, a surface in a volume. We have only 2D OH PLIF. That's why we can look only in this projection for the length of the flame front in a surface, in a unit surface. And this unit surface has been as well parametrically varied. In our case, at the end, it was 250 microns. And so there are two ways how to do this statistically. You have here's the wall, here's the instantaneous location of the flame. You divide your region of interest into these small volumes, similar to PIV. And now you look into each of these volumes whether there's a flame or not. If there is no flame, you take it as 0. If there is a flame, then you take the length. Yeah, you calculate simply the length in this control area. And then the flame surface density is the flame length divided by the area. That's the definition here. And then you have, up to the point where you have quenching, only one way to do it. Yeah? Either you have a flame in or you have no flame in. Downstream of that, you have two possibilities in your statistics. Either you consider the quenching, and you say then downstream of that you take them as zeros, and they're included in your statistics, or you say you ignore the quenching, and you just simply ignore that region downstream the quenching, and you say this is not a number. And this comes up then with different flame surface densities if you make the statistics. The conventional flame surface density, or that one considering that has been termed reactive flame surface densities by authors of previous papers. If you now go to the area where you have no quenching yet, the conventional definition of the flame surface density would be the same as the reactive one, but when you have quenching, of course, there will be a difference, and we will see how the difference is looking like. And so what I show now is the conventional and the reactive flame surface density shown here as probability of occurrence, independence of the distance from the wall. The wall would be 0 at 0. And that is done as well color-coded for different locations downstream the nozzle. At 19 millimeters, the quenching probability is 0, and you find both the definitions leading to the same results. And it's very sharp, because here this is more or less close to the flame holder. Although it's a turbulent flame, the wrinkling is not yet evolved. That's why it's very, very, very thin, the distribution. Now you go further downstream, and maybe I do this a bit faster, where you have then, it comes closer to the wall, and the distribution is getting broader on the expense of the height of that peak. So the differences start to shoot up when you're here in this region, where you see that the reactive flame surface density tends to 0, and the normal one expressing the laminarization, ignoring those downstream positions of the quenching, is shooting up. And whereas going even further at 48, the reactive one goes to 0, expressing that here the reaction has been terminated, it's quenched, whereas in the other definition you see still this laminarization up to the point where, of course, at some stage you don't have any flames anymore, and then you cannot go any further than this, let's say, 48 millimeters. Then you don't have any flames present any there. So that makes a difference. And interesting as well to compare that with DNS calculations for a very different setup that was head-on quenching, but they observed something very similar. Close to the wall then, the reactive flame surface density went to 0, and they see as well, starting from this typical distribution for turbulent flames, this laminarization in case of the conventional flame surface density. So we do have now two ways to calculate the flame surface density from qualitative OH data. And that has been done, of course, many times as well before us and without any walls. The question is now, we still need this quantity SL. SL, of course, the closer you come to the wall by heat losses, we have seen this in this simulation results earlier this morning, the flame speed slows down. And so how can we measure the flame speed? So first of all, I would like to show you a procedure how you can do it from simultaneous flame front tracking and velocity. And for that I use this branch of the phi flame which is not disturbed. Here is the flame front, and what we do now is we just go perpendicular ahead of the flame and determine here the velocity at this location. That is maybe now a millimeter displaced or so. And I would like to refer back to what we have used earlier for this turbulent displacement speed. We use the same idea now for the laminar one. Yeah? The overall flame propagation is the vectorial sum of convection and laminar flame speed. Yeah? You accept that again. And then we say this is a laminar stationary flame. That's why it doesn't move. So the overall flame propagation is 0. You throw that in here, and then you find, and you know that from I guess, combustion classes, when you have a stable Bunsen flame, for example, then your laminar flame speed must compensate the approaching convection speed. And so you now take at this blue line sufficiently far from the real flame front to avoid density effects, the same reason. You take the flame normal component, that is these small arrows, these green arrows. And these can be measured. And now you see, depending on where you take this isoline, this blue line, if you go too close to the OH, then you would find an SL value which is wrong. You have to go something like 0.9, 0.8 millimeter for these conditions ahead of the flame front, where you then reach the 0.38 meters per second that you know that should be achieved in premixed methane air at equivalence ratio 1. You got the idea? And then we have now a method where we think that is okay, going now to be safe 1 millimeter ahead of that, and we redo that for the other branch going close to the wall. Well, it's not perfect. Yeah? It's we have noise, unfortunately, but what I'm after is this decay. And according to literature, you can, as a reasonable assumption, say that the laminar flame speed is going to linearly to 0 when you go close to the wall. We cannot go closer than, let's say, this 1 millimeter, because we have to go 1 millimeter in front of that. Yeah, and that's a limitation. So you see here an extrapolation, and here inside an interpolation, which is far from being perfect, but is purely based on the experimental data, an estimate of the flame speed, the laminar flame speed, independence of the wall normal distance. And now we presume that holds true as well for the turbulent flame. It is only a slightly wrinkled flame, so the flamelet assumption will hold. And so when the flame eventually comes close, we know the flame speed by simply measuring the distance to the wall. That is the parameter. That is the lookup parameter with which we then have SL determined. And then we have this SL for each realization. We have the flame surface density, either the conventional or the reactive one. We know these two density and fuel mass fraction, and then we can determine here statistically the mean for the conventional flame surface density, using the conventional flame surface density to calculate the mean reaction rate, or do that with the reactive one which gives rise to this. And this is closer to the truth. The mean reaction rate approaches 0 when we are here at the location where the quenching probability has reached 1. Yeah? And so that is the correct number that should be used in modeling, and this is now quantified. Yeah? And this gives you an idea how you can make use of this data. Mean reaction rate experimentally determined the first time for this flame wall interaction. So this is just a short summary. As well, what I would like to point out is that we have observed a good agreement as well to this head-on quenching based on DNS 20 years back. And as well, we compare that to a model from Cambridge from first author was Watkins, and as well this results compared rather good with this model that has been here published. So we think that's a good way to deduce this quantity. Okay, so now we have a few minutes left and have a closer look into this thermochemical states. That has been now published in the meantime, so if you're interested in that, that's a combustion and flame article that is available online. Where we are now interested in, again, this region over here, sidewall quenching, but in terms of temperature and CO. So we concentrate really on this area over here, where we now do these experiments with local temperature and CO measurements, locally repeat the measurements in wall normal directions, and doing that for different axial heights. They are displaced from each other by 500 microns, and the step size in wall normal direction is 100 microns initially at least. And there you see now the temperature profiles. I go through them a bit faster. You see as well the CO profiles. The further downstream you go, the closer the flame actually comes. That is in accordance to this chemoluminescence. Of course, the chemoluminescence at some stage doesn't provide any information anymore because your temperature's reaction rate is already maybe too small that it's compensating against that background luminosity. Then we approach the region where we have at 50 millimeters. I go back. This is the closest point where the flame has come to the wall, because after that now you see the slope is decreasing, and that, as we know, is an indication that the direction has been switched off, and everything is only by transport effects causing this flattening of the profile. And looking at the CO profile as well comes closer and closer and closer. Eventually we're not able anymore to resolve here the CO boundary layer, and then as well we have for the highest position here, the purple one, the CO is going down because it's transported away and eventually still may react very slowly to CO2. So that already gives you an idea what's happening. Let's have a look now in a different perspective. So this mean profiles, you could look as well at variances. For the laminar case, it's not so exciting. However, that provides you an overall idea what's going on. But you do not really understand the detail. And that's why you have to go into these scatter plots. And so what I show you now is taking all the data at a certain axial height, 48 to 50.5 millimeters downstream the nozzle, and plot everything you have CO over T. So first of all, what you see is that each realization is confined to a small part here in the production of the CO and the consumption of the CO, and compares very well to a numerical simulation, a 1D flame simulation with full transport and chemistry. And that is maybe not astonishing because that information has been used for calibration. Yeah? So you see at 48 millimeters, no impact of the wall. So your measured data are looking very similar, maybe not here already, there might be some influence, but look very similar to an unbounded flame. And now the further you go downstream, the more ugly these scatter plots look like. Let's take 50 millimeters. So you see here overall a completely different pattern than in the undisturbed laminar flame, still this red line. the measured data look completely different. So let's have a closer look into them. How we can assess them. So first of all, we are not taking now all data at the given axial position, which is here 15 millimeters, but we condition now as well at the wall normal distance. So we make scatter plots at this height, being 100 microns from the wall, 200 microns from the wall, and so on later on. And because we do have a remaining fluctuation of that flame tip over here, it's not only in the state space, let's say one location that is accessed, because we fix now our probe volume, the flame is jittering around that. That's why you see different parts of the flame. That's why, because of that jittering, because of that fluctuation here, 100 plus minus 150 microns, you see these different states. And at 100 microns, you see here, the CO production and the CO consumption have been compressed to each other. These two branches, which are separated over temperature in a unbounded flame, separated, close to that wall, you see here the production, here the CO consumption, they come very close to each other. Yes?
So the previous slide that you showed, the scatter plots are all for the entire length of measurement along the y-axis?
Along the y-axis, yeah.
Okay.
These are along the y-axis.
Okay.
So just condition for axial heights, but taking all data from 100 microns to far away. And now this is here shown from 100 microns to 800 microns. And of course, at this height, the further you're away from the wall, the more you're in the burned gases. And it's quite interesting to see that if you're very close to the wall, 100 microns, both the CO production, this rising branch, and the falling branch, the CO consumption, both are influenced. The further you go away from the wall, you see the CO production is less influenced, but the CO consumption is strongly influenced still. And that holds true maybe up to maybe 700 microns. Here, nothing would, you're now in a location where you never have this CO production anymore. The jitter of the flame is not as large. It's only the CO consumption you see. And still, it's slightly shifted to smaller temperatures. And now the question arises, where does it come from? Why is this branch influenced only very close to the wall and the CO consumption already a millimeter away? And so the hypothesis is it's due to the time scales. It's due to the time scales because the CO consumption takes much longer. And if a process is much longer, then transport, heat diffusion, has a better chance to influence that compared to processes which are really fast. And that is now what I want to like to show you an argument that is supporting that. You can estimate a time scale of heat transfer based on a length scale, heat conductivity, density, and heat capacity. And this is done now here for the values of our mixture. We take the heat conductivity from that. We know heat capacity. We know density of the unburned mixtures. And we take as the characteristic length scale simply the distance from the wall. And if you do that, you end up with this parabolic shape. The time scale, the characteristic time scale of heat conduction is getting smaller and smaller the closer you come to the wall. And now you compare that to time scales taken from 1D flame calculations for CO production and CO oxidation, and you find the CO production is roughly an order of magnitude faster, that is this value over here, compared to the CO consumption. And then you see at this location, at roughly 0.2 millimeters, that is where the heat transfer becomes to be faster than the CO production. For the other distances, all times, it seems to be that the characteristic time scales for conduction are faster than the CO oxidation, meaning that for all these distances, the CO oxidation is influenced by heat transfer, whereas you have to go as close as roughly 200 microns to the wall until the heat conduction is fast enough to influence the CO production. I go back, and that is seen. Yeah? At 100 microns, you see for both branches the impact, whereas for beyond 200 microns, it's only the CO consumption. That is a rough explanation what's going on. Of course, you would like to do that as well in a simulation, compare that, and Maybe a few words about that comes in a second. But still, what we have not really done is we have not deconvoluted from the intermittency. And that's still something which is not good. Because in the end, it doesn't matter where you are in the lab space. In the end, it does matter only where you're in the reference frame of the flame. And that's why we take advantage as well now of the simultaneous information of the flame front taken from OH. So as I've shown, you can determine where the flame quenches. And then eventually, because of that fluctuation, eventually you have situations where your probe volume looking for the CO and the temperature is upstream the quenching point. And then you can measure that distance, delta Z. At a next realization, where the flame has now maybe moved to a lower position where it's quenched, then your COT measurement position is downstream that realization. Then this is called minus delta Z. So everything is now referenced against the location of the quenching point, because we assume the flame doesn't behave differently dependent on the axial height of quenching. We just say relative to the quenching, that is the important quantity. So that again means a conditional average. I come back to yesterday. It means you're using that qualitative information from OH to identify a reference point and then do conditional statistics to that. And then you have a pre-quenching when COT is measured upstream, post-quenching when it's measured downstream. You measure at the quenching point if delta Z is 0. And then you see here the data. The pre-quenching, this is 0.5 millimeter upstream. Again, red, the laminar flame calculation, and the black dots are the measurements, and green are the conditional mean from these measurements. And that looks like an undisturbed flame. But now look, if you're at the quenching, this is 50 microns from the quenching only, everything looks very different. Yeah? So here you see that at the quenching point, the scatter plot looks completely different. And that needs to be accounted for. If you would now use a similar flamelets model with tabulated flamelets close to the wall, they would not represent what happens in reality. And if you go then downstream in the post-quenching region, everything goes down to the chemical equilibrium, as you would expect. And we have used now this experimental data to feed that into a 2D DNS to simulate exactly what's going on. And this is shown here in the blue line from the DNS calculations. These calculations follow more or less very closely to what we measure. And now using this DNS shows, similar to what we have estimated experimentally, that the diffusion is the dominant part of this phenomenon. It's not the chemical kinetics. Yeah, it's not that the heat transfer by cooling down the gas samples and thereby has an impact on the chemical kinetics. This is the main reason for this fuel. Because you would maybe assume that if you have, let's say, everything cooled down to 1000 K, that then low temperature chemistry kicks in. It does not for methane air. It's not expected as well for methane air. If you would go for another fuel, I don't know, maybe then you have as well low temperature chemistry effects kicking in addition to this heat transfer effects. But that is, I would say, as well, clearly showing with the experiment we can give directions. We can see what is actually happening. But as well maybe make a hypothesis on why that actually is happening. In the end, we have to compare that with models that account for these effects and then have much more parameters to be used for a full understanding, which is then needed later on for reduced modeling in RANS or large eddy simulations. So I have no time to go into the turbulent case. Actually, we have not really digged into that as well. Everything you can see is very similar, although now the state space is more evenly filled with realization as well in between. So because of the time, and I would like to keep some minutes as well for discussion, I would like to skip that. Because I think early on this week, there was as well a question about this, who asked that, about 1D cars. And that is maybe something we should use another couple of minutes before opening the session as well again for questions. So forgive me to overgo these conclusions. Maybe one point only. combustion modeling needs to account for this near wall effects. So using simply the approaches based on flamelet modeling, flamelet generated manifolds, or whatever the name is, would not be a good choice. You have to extend that at least by the non-adibacity, by the heat losses. Okay, open issues. In this regard, you really need to resolve all the boundary layers. That's clear. Everything is getting so small. And then, as I've shown or expressed at several times, experiments on their own are not sufficient. You need theory, you need modeling, and you need the simulation in the end. And then only you have a chance to get a more comprehensive understanding. But without experiments, of course, you are lost as well, because you have to show that the theory and modeling is really representing what has been measured. That's extremely important, the coherent action of these things. And as I said, these near-wall turbulent combustion models need to be developed, and that is currently ongoing. Of course, it becomes even more interesting if you have wetted surfaces, if you have deposit formation, very important aspects in reality. And so we have only scratched the surface so far. There's a lot of open questions. And so I would say combustion research is not dead. Yeah? There's a lot of interesting problems that are completely open to you guys for your career. But as there was the interest in more sophisticated cars than we have available, I would like to use the chance as well to advertise what Chris Cleaver is doing at the Sandia National Labs. He came up with a possibility to measure 1D temperature profiles with the 1D cars. So now at the end of this week, we're coming back to sophisticated diagnostics. That's maybe good. And that is what I wanted to stress. Of course, there are other things which are very important to measure, like scalar fluxes, but I'll leave that out here. So this is the approach from Chris Cleaver. He is doing rotational cars, and he's doing that by using only 2 beams. In that sense, it's easier, but these 2 beams are, one of them is a femtosecond laser. This is here the femtosecond laser, 45 femtoseconds, that green guy over here. And that is used one and the same beam for pump and Stokes. He drives Raman coherences within the same vibrational state that's not changed, delta V equals 0. He drives only Raman coherences based on the selection rule we discussed earlier, delta J equals 2. Meaning that he brings it up to the virtual state and then immediately brings it down to a different rotational state. And thereby you get the rotational structure probed with this beam over here, which is 70 picosecond. That's why he calls it hybrid, picosecond, femtosecond. And under a relatively large angle, where still the phase matching is fulfilled, because of that large angle, you have here this intersection of these focused beams, 2 cylindrical lenses, with a resolution along that line. And because of that focusing as well, very, very thin. And so the best, I'm not sure about the best numbers he reported. It's in the order of 50 to 60 microns resolution along that line. And then he detects that, and using polarization to get rid of that pump of that probe beam over here, that then is measured in a conventional spectrometer. And we had the chance to use that facility at the Sandia National Labs. We brought our flame wall interaction burner to that. And that was here Christopher Jainski, who finished his PhD recently, working with Alex Bolin and Chris Cleaver in the labs there. And there you see the position, a wall normal position. So sorry, this is not Y as it should be in fluid mechanics. Chris is a chemist, that's why he takes an X. You see the temperature. You see that for different equivalence ratios, that's shown over here, from lean over stoichiometric to rich, with these different colors. And you see how when you now come to the position where you have flame quenching, that it was set here to 0, then you see how the, what is that? This is the temperature near 40 microns from the wall only. How 40 microns from the wall, here the temperature goes up and reaches really high values, and that would be the approaching, here would be the quenching, and here would be then the diffusion, the transport part, the post-quenching. And you see here as well these dashed lines. Those are the positions using a 1000 Kelvin isocontour where it comes closer and closer to the wall, to the quenching, and then bounces off because of diffusion. And all this information along that line has been achieved in a single shot. Here it has been now averaged, but the potential is now proven that this can be used as well for turbulent cases. And that's really a huge step forward. If you now have a temperature profile along a couple of 2 millimeters or so with a 50, 60 micron resolution and really resolve thermal boundary layers, that's great. That's great. But it's a rather complex system. Because you have a femto and a picosecond laser. Okay? And with that, I hope you're as fascinated as I am from this great facility. There is still a lot of room, as I said, where you can make a huge impact using this nice diagnostics. But if you do that, always link up with theory and modeling and simulation. Okay, so first of all, before we have still maybe time for a few questions, I would like to thank you. You have been a great audience. I really appreciated all your questions and appreciated that actually I have no one seen sleeping and that you stayed with me 15 hours, which is very exhaustive. I know that. So thank you very much. So. Thank you.
Thank you so much.
So we have to postpone the question. Okay, have we time for a question?
Yeah, question.
Yeah? Questions? Yes, yes.
So for the 40 micrometer,
Yeah?
which layer of the boundary layer do you use? Is it the viscous, buffer, or industrial layer?
Oh, the question was about what we can resolve within this boundary layers, whether the 40 microns is sufficient to look within to the sublayers. And the viscous layer, I would say, for this case, would be resolved. With the 40 microns, I would expect, yes. I think it's sufficient for that. Who was first? You.
Okay, diffusion, that's species diffusion that dominates, not thermal diffusion.
The question is whether thermal or species diffusion. That is what we see when we, of course, look for the temperature is the thermal diffusion. Right. But of course, for the CO that we observe for the different temperatures, that is the species diffusion.
And that's what's the driver.
Yes, that's the difference as well to the that we observe then for the unbounded flame. Okay.
So yesterday we were talking about Raman scattering, and the procedure that we did was we actually assumed the temperature, and then we went about doing the repetitive, so we did some sort of iterative methods to get these solution for the species that were there. Is there a way for us to do like cards and Raman scattering, polished or something like that?
Yeah.
With a small delta T, if you will.
So when I got the question correctly, whether it's possible to combine something like Raman spectroscopy with cars,
Yeah.
close to the wall, or independent?
Independently.
Yeah, of course. You could use that, but it comes with a huge experimental effort then. If you take the 1D cars and overlay there the 1D Raman, in principle you can do that, but I doubt that anyone has the budget or as well. It will be painful, I guess. So in principle, yes, but in practice, I would say it will take some time until we see that. Okay, Isahar?
In the slide that you showed a CO scatter, there was a fringes of CO scatter data. Was it peak clogging or something physical?
Okay, the question was why we do have always certain areas in the scatter plot that have been covered. That is due to the fact that we have measured spatially at 100 microns and at 200 microns and at 300 microns. And that's in that sense locking due to the location where we have done the measurements. Yeah, if you do it, if you would perform that now 1D, you wouldn't see it anymore. Yeah. Yes.
For your open question, you say you have the decoupling, that means your neo is become the multi-phase problem, not the single phase problem.
Yeah, the question is what is about the deposits if you have them, if it becomes a multi-phase problem. It is multi-phase anyhow, you have gas and solid. But now if you're talking about deposits that develop typically then as well from a liquid, so it's even more complicated, but happens. For example, in exhaust gas after treatment systems, for example, where you spray in urea, yeah, that would be as well a very nice and challenging environment where from the liquid phase then you eventually see a crystallization and deposit formation. And then you have as well, in addition to that, a liquid phase and a crystallization. And then it becomes a even more multi-phase problem for the future.
For your conclusion, you say dominance diffusion.
For that case, yes.
Yeah. That means your problem will become to is fluid mechanics near the wall, right?
Yeah, not only, because that heat transfer changes as well your flame structures. And that means if you now model a turbulent flame that has been done for a lot of time for premixed flames for their turbulence levels with flame modeling or so, as I mentioned, then these lookup tables used for that, assuming a certain structure, is not valid anymore. The flame structure changes. The flame structure is at the wall or close to the wall, different than remote from the wall. And that needs to be accounted for. And that is not included in the models yet. Okay. So I think we're done. So thank you once again.
Yeah. No, what it says really, no one doses off. I've been watching. It's not even 3 hours, 15 hours. Good for you guys.
Okay, thanks.